In this video, we're going to work example problems on acid-base titrations. So what we're doing with titrations, so acid-base titrations or redox titrations, and with gravimetric analysis in this chapter is we're performing stoichiometry, or more specifically with titrations and gravimetric analysis, we're performing quantitative analysis on reactions in aqueous solution. Gravimetric analysis and titration are techniques for determining amounts or concentrations of a substance involved in a reaction in solution. Okay, now with a titration, what we're doing is we're determining the unknown concentration of some solute in solution. That's the goal of a titration. And with an acid-base titration, so the example problems we're working in this video, the goal is to determine the unknown concentration of an acid or base. And to do this, what we do is we titrate the acid or base solution of unknown concentration against an acid or base solution of known concentration that's called the standard solution. So in an acid-base titration, the quantitative analysis is centered around an acid-base neutralization reaction. You can compare this to the gravimetric analysis problems we worked in a few videos ago, in which the analysis was centered around a precipitation reaction. So, okay, describe the steps involved in an acid-base titration. And why is this technique of practical value? All right, so let's go through the acid-base titration process. The general idea is you've got a scaled burette here that feeds solution into the flask below. It's not like a titration has to be set up exactly this way, but this is the general idea. Okay, and you're going to have the unknown concentration solution in the burette and the standard solution in the flask, or vice versa. So like the unknown solution could be the acid or the base, and it could be in the burette or the flask, or vice versa. It doesn't matter what solution is in the burette or the flask, and whether or not the acid or base is in the burette or flask, doesn't matter. Okay, but now you want to note, though, as we talked about when going through this section of the textbook, we're only considering titrations, acid-base titrations, in which at least one of the solutions is strong. At least one of the solutions contains a strong acid or base. The unknown solution or the standard solution, one is going to be a strong electrolyte. It's not like a titration couldn't potentially be done titrating a weak acid or base against a weak acid or base, but that's more of an advanced topic that we'll talk about in chapter 16. So like the textbook mentioned how a common acid chosen as the acid for the standard solution when titrating a basic solution is potassium hydrogen phthalate, or KHP, which is a weak acid. Therefore, any problems we work in this video, in this section where KHP is the standard solution, are going to involve titrating a strong base solution. Okay, so in the example the textbook gave, which that's what this picture is from, main example the textbook gave, in the flask was a KHP solution, an acidic KHP solution. KHP is an acid, and in the burette was the unknown solution, the solution of unknown concentration, which was a sodium hydroxide solution, NaOH. Therefore, the goal of the titration was to determine the concentration of NaOH or OH minus in the basic solution, right? You could say, I could have said that as the concentration of either NaOH, or I could say the concentration of OH minus ions, and that would be actually the same value. However, for example, if we were dealing with barium hydroxide, we were trying to titrate a barium hydroxide solution, then saying the concentration of BaOH2 or the concentration of OH minus ions would actually be two different values. But like once you've determined one of those concentrations, you've actually automatically determined the other, so it's just however you want to state it. When we learn about pH in chapter 15, we'll see that the best way to state the concentration in this case would be in terms of pH, which is pH is a function of the concentration of OH minus or H plus ions in solution. But right now for these problems, we're not thinking about pH, and so it doesn't matter in terms of referencing the concentration of the standard solution or the unknown solution. We're just going to think about this in terms of the original substance that was dissolved, so the concentration of KHP or the concentration of NaOH. Okay, but now when preparing the standard solution, or in this case that would be the KHP solution, which remember, when I say that, I'm circling around the flask here, but the standard solution, you could have put the standard solution in the burette if you wanted to, but regardless, for the standard solution, you're going to need to weigh and record the mass of solute that was dissolved. So in this case, for this experiment, that would be the mass of the KHP. Here's KHP. You would weigh out a certain mass of KHP and then dissolve all of that in water, and that's the solution, in this case, in the flask. Now, you don't need to measure the volume of the standard solution. How much water you used here to create the standard solution, it doesn't matter. As long as it only matters in the sense that you need to have enough to ensure that all of the KHP gets dissolved, or all of the, whatever the standard solution solute is, gets dissolved. And therefore, solubility with respect to like saturation points could come into play. However, just like we talked about with gravimetric analysis a few videos ago, we're assuming for these problems in this chapter that there's no solubility issues. We'll talk about solubility equilibrium with respect to titrations in chapter 16. Okay, so they've got the standard KHP solution in the flask, and the mass of KHP dissolved in this solution is recorded, and in the burette is the unknown sodium hydroxide solution, unknown concentration. Now, for titrations, we're going to be tracking the volume of solution that's added from the burette. Whether or not in the burette is the standard solution or the unknown solution, we're going to need to be tracking the volume of solution added. And that's the purpose of the scale on the burette. We're going to track the volume using the scale and using this valve here to slowly add. You don't want to add it too fast. And so, like, remember, this is different from the gravimetric analysis in that it was only important in the gravimetric analysis that we didn't add too little of one solution to the other. But we could add excess. In fact, in that case, we wanted to add excess or more than was necessary, but we weren't even tracking, though, how much solution was added. Here we are. Okay, and so the idea then is the titration is started by slowly adding burette solution to the flask, just slightly opening the valve and slowly adding burette solution. And as the solutions are mixed, the corresponding acid-base neutralization reaction that the titration is centered about takes place. In this case, the hydroxide ions from the burette solution are going to be interacting with the H plus ions from the flask solution, and they're going to neutralize. They're going to come together to form just more water. Okay, so like you want to think about how, in this case here, we're starting with an acidic solution in the flask, right? It's got the KHP dissolved. Then when the burette solution, the basic burette solution is added, all of a sudden you introduce some OH minus ions into the solution, but the H plus ions consume those OH minus ions. And then what happens is, in this case, since we're dealing with the acid in the flask as a weak acid, you have the H plus ions in the acidic solution consume all of the OH minus ions, and then now you've got an absence of H plus ions, and that drives the weak acid reaction, reversible reaction forward to where more of that KHP then disassociates into more H plus ions. Okay, and so once you've added a little bit of the burette solution and the reaction takes place and it comes back to equilibrium, you're left with an acidic solution again in the flask. You started with an acidic solution, you added a little bit of burette solution, and you're ending with an acidic solution. Okay, and then as you continue to add more and more burette solution, the same process happens. You get more OH minus ions in the flask, but all the H plus just consumes them, gets rid of them. Until at some point, you're going to be running out of the KHP acid molecules to keep replenishing the H plus ions, right? And once you get to the point that's called the equivalence point, where it's like you could think about theoretically the moment in which all of the KHP molecules are gone, then when you add another drop of the burette solution, the NaOH solution, you're going to have the OH minus ions are going to come into the solution, but there's not going to be any H plus ions to consume them. So now you've got free OH minus ions in the solution with no H plus ions. So the solution is now basic. At the equivalence point, the flask solution has switched from acidic to basic. Again, this point is called the equivalence point. And with a titration, you want to stop adding burette solution to the flask solution as close to the equivalence point as possible. Okay, and then with titrations, a general titration, all titrations, whether it be acid-base or redox titrations, are going to have this equivalence point, and the equivalence point is identified with some sort of indicator. In an acid-base titration, an indicator is going to be a substance that has a distinctly different color in acidic and basic media. A commonly used indicator for this purpose with like an acid-base indicator is phenolphthalein, which is being used here in this titration. Phenolphthalein is colorless in acidic and neutral solutions, but reddish pink in basic solutions. So once you get to the equivalence point and you're going really slow and you add that next drop of the burette solution, you'll see a colorless solution, then you add one more drop, and then you'll see it starts to get pink very quickly. And that's when you know to stop, right? This is switched from acidic to basic, which is what the phenolphthalein is showing you. Okay, so now the titration is complete. You stop the titration, and the next step is you record how much of the burette solution was added to get to the equivalence point, the volume of the burette solution. Okay, and so now you have all of the information you need to determine the concentration of the unknown solution. Because what you do next is you write out the balanced acid-base neutralization reaction. And you can think about how with titrations, you're going to be able to write out this entire chemical equation that the analysis is centered about, because you know the compositions of both solutions involved. Like for the unknown solution, we know it's a sodium hydroxide solution. We just don't know its concentration. But like you can compare this to the gravimetric analysis problems we worked. That analysis was centered around a precipitation reaction, but we couldn't write out the full balanced equation for that precipitation reaction because we didn't know the composition of the unknown substance. Well, actually, we did talk about certain applications of gravimetric analysis where you're trying to determine the purity of a substance of known composition. So in that case, you could actually write out the full equation for the precipitation reaction, but you're not going to need it. Okay, but for the main application we talked about, in which the unknown was the exact composition of some compound, then you can't write out the precipitation reaction, right? Okay, but again, here, when it comes to titrations, when we're done with the titration, we know how much mass of the standard solution substance, in this case KHP, was dissolved to create the standard solution, and we know the volume of burette solution, in this case that's the unknown sodium hydroxide solution, that was added to get to the equivalence point. And so the next step is you're going to write out the balanced acid-base neutralization reaction, and specifically this is going to be the molecular equation, not so much the ionic or net ionic equation. You're going to want to reference the molecular equation here because, remember, the molecular equation gives you the best visual for the original substances or compounds that were involved to make everything take place, which is what we're interested in here. The ionic equation could be useful as well, but the net ionic equation might not be as useful in this case because, like, for example, if you were titrating with a strong acid and a strong base, then the net ionic equation is just going to be, it's like H plus aqueous plus OH minus aqueous gives liquid H2O. So you lose all of the information about where the H plus and the OH minus ions came from, which is what we need here. Okay, So now, but once you have the balanced molecular equation, then so you know how much mass of the standard solution, acid or base, was started with. And the key to all of this is that you also know how that entire mass of acid or base was stoichiometrically consumed in the reaction. So like the reaction is stoichiometric in that there's no limiting or excess reagent here, because the reaction was stopped at the equivalence point, as close to as precise of the amount of NaOH solution that was needed to react with that exact mass of KHP was added from the burette. So all you need to do is use stoichiometry to determine how many moles of sodium hydroxide stoichiometrically reacted with that many grams of KHP. And you know that's how many moles of NaOH must have been added to the flask from the burette, added to the KHP solution. Okay, but with that information, we also recorded how much volume of the NaOH solution was added to the flask, right? From the burette. So all you do is just divide that number of moles of NaOH by the volume that was added to get the concentration of the NaOH solution, which is what we're looking for. Okay, so that's the acid-base titration process. Okay, a student carried out 2 titrations using sodium hydroxide, a sodium hydroxide solution of unknown concentration in the burette. So it's this same type of titration we just talked about. In one titration, she weighed out 0.2458 grams of KHP and transferred it to an Erlenmeyer flask. She then added 20 milliliters of distilled water to dissolve the acid. In the other titration, she weighed out 0.2507 grams of KHP, but added 40 milliliters of distilled water to dissolve the acid. Assuming no experimental error, would she obtain the same result for the concentration of the sodium hydroxide solution? So, okay, let's think about what this question is asking. So it's talking obviously about an acid-base titration. And, okay, what's the goal of an acid-base titration? The goal is to determine the concentration, the acid or base concentration of some unknown acid or base solution. That's the goal. So here we can see that it's titration we just talked about. The standard solution is the KHP solution, and the unknown solution is the sodium hydroxide basic solution. So the goal here for this titration is to determine the concentration of sodium hydroxide in the sodium hydroxide solution. Okay, and so then the question then is, when they're saying that, assuming no experimental error, would she obtain the same result for the concentration of the NaOH solution? So if you think about what that question is asking, you could think about how, so let's say this student, this girl, only did one titration on that solution, and then someone else comes in the next day and is going to do their own titration on that same NaOH solution. Well, okay, they could potentially do the titration different ways, take different paths, but they should get the same answer, right? They're both looking to get the concentration of sodium hydroxide in the exact same sodium hydroxide solution. So then the question then is, with these 2 different paths, where it says the KHP solution was, the standard solution was this many grams of KHP and this many milliliters of water, and then she did another method, which you could think about as like another student coming on day 2 and using the standard solution was this many grams of KHP and this much water. The question then really is, if both of these paths are valid paths, then the answer is yes, you're going to get the same result. So what would make one of these, either of these 2, invalid? Which these 2 methods are just the way the standard solution, the standard KHP solution is prepared. Well, it's just going to be, that would be the solubility issue, right? It's just like, is 20 milliliters of water enough to dissolve all of this? That's the only criteria. All of this needs to dissolve. We don't care how much volume of the total volume of the standard solution is. We're just tracking how many grams of the KHP were dissolved. And same over here. And we don't have to, we can choose any amount of KHP we want. The mass of it doesn't matter. And again, the volume of the water doesn't matter either, as long as all of it gets dissolved. So the answer is, yeah, the same result's going to be obtained. Yeah, like with these different test setups, you're going to need to add a different amount of sodium hydroxide from the burette, but so what? it's all going to equal out to, you're going to get the same concentration of the solution, the unknown solution. Okay, would the volume of a 0.1 molarity sodium hydroxide solution needed to titrate 25 milliliters of a 0.1 molarity nitrous acid, a weak acid solution, be different from that needed to titrate 25 milliliters of a 0.1 molarity hydrochloric acid, a strong acid solution? Okay, so this is another theoretical question. We aren't going to be doing any calculations here. And what this problem is asking about is the effect of having two strong electrolytes in the titration, so a strong acid and a strong base, versus having one of the solutions, either the unknown or standard solution, contain a weak acid or weak base. All right, and so if we just take a look at the way this is described here, the sodium hydroxide solution in this case is actually the standard solution because we're titrating these two acids. In the previous problem, we were titrating the sodium hydroxide solution. Okay, and here we're thinking about two separate titrations. For the first titration, they're saying that 25 milliliters of a 0.1 molarity nitrous acid solution was needed to get to the equivalence point. For the second titration, they're saying that also 25 milliliters of a 0.1 molarity, but in this case, a hydrochloric acid solution was needed to get to the equivalence point. So for both titrations, it turns out to be the case that both unknown solutions have the same concentration, and also both unknown solutions consumed the same volume of solution to get to the equivalence point. And the question is that, is it the case that the corresponding standard solution volume consumed in these titrations would be the same? Now, this is kind of confusing. You might be thinking, well, I thought we didn't track the volume of the standard solution. All we did was measure how much mass of standard solution solute was dissolved, right? And yes, that's true, but it could be the case that you do need to track the volume of standard solution, because we can think about, so I mentioned how you could put the standard solution in the burette if you wanted to, with the unknown solution in the flask. And that's kind of how we might want to think about this problem here, in that we're adding the standard solution. Again, and this is kind of confusing. In this case, the sodium hydroxide is the standard solution, not the unknown, but we're adding the standard solution from the burette because we're thinking about how much volume of standard solution was needed to complete the titration. And so if we think about it from that perspective, so we've got these two separate titrations, and we're going to put the unknown acidic solutions in the beaker and the standard basic solution in the burette. And so in that case, we're going to need to measure how much volume of solution was put into the beaker, right? Because you have to know the total volume of unknown solution that's involved in the titration. So you would measure out, in both cases, you're going to put, they're putting 25 milliliters of the unknown acidic solutions into the beaker. Okay, but then with the standard solution in the burette, you could think about how you would prepare the standard solution in its own beaker off to the side and then pour that into the burette. Well, in that case, what you would need to do is, because in the titration, we're not going to be using all of the burette solution. You're going to be adding the burette solution slowly until you get to the equivalence point. So we're going to have to be tracking the volume of total burette solution added. So what you would need to do then is, when you're preparing the standard solution in its own separate beaker off to the side, you would measure the mass of the standard solution solute dissolved, convert that to moles, and then divide that by whatever the volume of water was used to make the solution. So now you have the concentration of the standard solution. You pour all of that into the burette. You track exactly how much burette solution was added to get to the equivalence point. And then at the end, when you're doing stoichiometry on the chemical equation, you just take that total volume of burette solution used and combine that with the known concentration of the standard solution that you calculated to get the total number of moles of the standard solution solute that was consumed in the titration. Okay, and so, but coming back to the question is, for these two separate titrations, where you've got these two acidic solutions being titrated, one is a strong acid and one is a weak acid, and you're putting these quote-unquote unknown solutions into the beaker, In each case, 25 milliliters. And in each case, you know that both of those solutions have the same concentration of 0.1 molarity. And then in the burette was the standard basic solution with this strong base, sodium hydroxide, and its concentration was also 0.1 molarity. You knew this. Then to get to the equivalence point, is it going to be the case that the volume of the standard solution added from the burette is the same volume for both titrations? If both of these acids were strong acids, we would automatically just say yes. So this question is really about what effect does one of these unknown solutions being a weak acid and one being a strong acid have on the titration? And the answer is it doesn't have an effect. The volume of standard solution added is going to theoretically be the same in both cases for both titrations. Because, yes, initially before the titration starts, in the beaker with the hydrochloric acid, you're going to have more H plus ions than the nitrous acid. Because with the hydrochloric acid, the strong acid, every single mole of HCl dissociates from the beginning, right? But that's not the case with the nitrous acid. But it's just like I described earlier. With the weak acid, when the two solutions are mixed and the H plus ions start getting consumed, the absence of H plus ions in the solution pushes the reversible weak acid reaction forward. The weak acid reaction is going to continue to be pushed forward as H plus ions are neutralized out of the solution. This reaction is going to be pushed forward all the way up to the point when the last nitrous acid molecule dissociates. So just like with the HCl, the strong acid, every mole of the nitrous acid is theoretically going to be involved in the titration. Now, but something to note, though, is that titrations involving a weak acid or a base are known to have less sharp of an equivalence point than titrations involving both a strong acid and a strong base, which can make identifying the precise volume of burette solution needed to get to the equivalence point more difficult. However, theoretically, the volume of the sodium hydroxide solution added to get to the equivalence point is the same for both of these titrations. Calculate the concentration in molarity of a sodium hydroxide solution if 25 milliliters of the solution are needed to neutralize 17.4 milliliters of a 0.312 molarity hydrochloric acid solution. Okay, so we don't know the concentration of the sodium hydroxide solution here, so we can assume that we're titrating this solution, and we're using this hydrochloric acid solution as the standard solution. And we can think about this as, since it's telling us that we used 17.4 milliliters of this standard solution, it's kind of like we were adding it from the burette. I mean, you could look at this from the other perspective. I mean, they give us the volume of the sodium hydroxide solution as well. But regardless, we know the concentration of the standard solution, and we know the volume that was of the standard solution that was either initially in the beaker or that was added from the burette. And so we can, no matter how it's set up, we can easily get the number of moles of the standard solution substance that were involved in the titration. So let's go ahead and do that. If we've got 0.312 molarity of this is hydrochloric acid, we know that molarity is moles per liter. So this is moles of HCl per liter of solution. So this is 0.0174. So, okay, the moles of hydrochloric acid that were involved in this titration is 0.005429. Okay, now that we have this information, let's go ahead and write out the molecular equation for this reaction. So this acid-base neutralization reaction. So we've got HCl aqueous and NaOH aqueous, and now we've got a with the acid-base neutralization, we're going to have a salt and water, right? So NaCl, and we would want to check to see if perhaps this is a precipitate. We know NaCl is aqueous, and then water. Okay, but now we're not done. We need to balance this. So you've got two H's on the left, two on the right, one oxygen on the left, one on the right. Sodium. Okay, yeah, this is balanced. So there's the molecular equation. So now we've got this here. Right? So all we need to do is, since we know that this entire reaction, it was stoichiometric, there's no limiting reagent or excess reagent, we just need to, okay, well, how many, if this many moles of HCl were consumed, well, then how many moles of NaOH were consumed? So that's just, right? You use stoichiometric equivalencies for every, but you need to write out the molecular equation and balance it, because it might, here it's just, okay, for every 1 mole of HCl consumed, 1 mole of NaOH was consumed, but it might not be a 1-to-1 ratio, right? So, okay, there we go. So you take this, it's just 0.00. Okay, so this many moles of sodium hydroxide were involved in the titration. Well, all of this came from this volume here, this 25 milliliters. So the concentration of NaOH in the unknown solution is just take this and divide it by 0.025 liters. .217. What volume of a 0.5 molarity hydrochloric acid solution is needed to neutralize each of the following? Okay, so part A. Okay, so, which of these is the standard solution, which is the unknown solution? It really doesn't matter. We know that, okay, we've got 10 milliliters of a 0.3 molarity sodium hydroxide solution. So we can get the number of moles of sodium hydroxide that were involved in the titration. So that might suggest that this is the standard solution, but it might not be the way they worded this. It kind of sounds like this is the standard solution, but it really doesn't matter. If we've got a 0.3 molarity sodium hydroxide solution, and we're thinking about there's 10 milliliters of this solution, so that's 0.01 liters, well, how many moles of sodium hydroxide are in that solution? So 0.01 times 0.3, 0.003 moles. Okay, so now we can, this is kind of confusing because they're asking us a question about the volume added, so we're not going about this in the standard, kind of the standard step-by-step way we would do for a titration process, but we can think about how, so we've got the number of moles of a certain substance involved in this titration, so let's go ahead and write out the molecular equation here for the neutralization. So, okay, you've got HCl. This is the same as the previous problem. And the salt is okay, so we've got this, right? So let's just use stoichiometry to get here. Why not? So moles of NaOH times the fact that for every 1 mole of NaOH consumed, 1 mole of HCl was consumed. So now we've got the number of moles of HCl involved in the titration, 0.003. So, but we know that this solution here with the HCl, we know its concentration, so we can just solve for the volume because molarity is equal to N divided by V. So that's going to be V is equal to N divided by M. So just take 0.003 and divide it by 0.5. And then we can put this in milliliters. So 6 milliliters. Okay, part B, this is the same question, but we've got this barium hydroxide, and so this is where writing out the molecular equation is going to be helpful. So, okay, we can just get the number of moles of barium hydroxide, so 0.2 molarity .01, so we've got, let's see, 0.01 times 0.2, 0.002. Okay, now let's write out the molecular equation. So we've got HCl plus then the salt is going to be barium chloride, which we could check the solubility chart. Why not? So all halides are soluble and barium's not an exception. And then water. So now we need to balance this, but okay, wait, no, this is BaCl2 because you have Ba2 plus and Cl minus. Okay, so balancing this, we've got, need a 2 here to balance the chlorines. Now you have 4 hydrogens on the left, 4 on the right, 2 oxygens on the left, 2 on the right, 1 barium on the left, 1 on the right. So that's balanced. Okay, so, but here you've got 0.002 moles. So, okay, 0.002 moles of barium hydroxide. So what is, if this many moles of barium hydroxide were consumed, then what does that translate to with hydrochloric acid? So for every 1 mole of barium hydroxide consumed, 2 moles of hydrochloric acid were consumed. And so there were 0.004 moles of hydrochloric acid involved in this titration. So, okay, you just, molarity is, so V is, divide this by 0.5. That's 8 milliliters.